I will begin with a word of prayer. All right. Heavenly Father, we thank you for this day again. I thank you for this class. Just ask you to guide our steps today. Help us to understand what we're doing, Lord. In your name I pray, Lord Jesus. Amen. So, if you missed last class, well, good for you, I guess. So, I will, maybe I'll post it. I don't know. I got to think about it. I don't know. What's that? No, that was intentional. I haven't yet reached the point in my life I can post that video. I need to look at it again. Maybe it's not as bad as I remember. But anyway, let's talk about orthogonality again. I mean, there are some things we did last time which have value, and I don't really want to redo them today. So, but let me at least start in the right direction. So let's talk about projections. So the first kind of projection you might talk about, if you were doing things more logically, might be this. Like, here's A, and here's B, right? And so, how do you find, there's clearly a vector here, which we should be able to construct, and we can call that the projection onto the A direction of B, all right? And like, what's the formula for that? Well, let me just take a step back and try to motivate that a little bit with, just think about three-dimensional geometry for a second here. If we think about, X, Y, and Z, and I could do it two-dimensionally, but I think three dimensions nice. If we take a vector, right, out to here, we can build that in three pieces, right? So we've got like this piece, right? And there's this piece, right? And then of course there's, oh my goodness, this piece, right? And so if I call this vector B for the sake of discussion here, well, you guys know the deal. B in three dimensions we can write as like B1, B2, B3, right? Which you could also write as B1 times 1, 0, 0 plus B2 times 0, 1, 0 plus B3 times 0, 0, 1, right? Now, respectively, like that's the red part and the green part and the blue part. These are respectively, you could call this, it's the projection in the x hat direction. Well, I guess we use E1 in here, don't we? So in the E1 direction of B, right? For example. And so like the formula for that, if you look at it, is really, well, it's B1, E1, right? But how would you express that in terms of dot products? Well, think about it. This is really B vector dot E1 times E1, isn't it? And if you look at it, the other one, say projection. I've forgone my color coding now, so don't try to read into the color coding at this point. My apologies. But the Y part is like B2, E2, right? And again, this will work. I take the dot product of B with E2, and then I put it in the E2 direction. Like that's the vector projection of the vector B into the Y direction, into the second direction, right? All right? So there's really nothing special about X and Y and Z directions. So what should the formula be here, if we're going in an arbitrary, we're trying to project B into an arbitrary A direction, what's the formula? Well, it's just the same idea, but this time we do B dot A hat in the A hat direction. What's A hat? Well, A hat, by definition, is A divided by the length of A. Now, I do have to assume something here, right? Which is what? A had better be non-zero, otherwise we're in trouble, right? But if A is non-zero, then you can write down this formula like this. Now, if we write that instead of with A hat, with A, what's the formula look like? Yowzers! We've got, let's see here, B dot A divided by A dot A, right? So there's a formula without the unit vector A for the projection. But this is just the projection onto a single direction, right? Now what was the other thing we talked about? We also talked about the orthogonal projection last time, right? But I jumped straight from the basic thing to like the most like the general version of it. I should have done the basic thing first last time, like this, right? I should have started here. My bad. But this vector perpendicular right here, right? This is what I would call orth A of B, all right? And the basic, you can see it in terms of vector addition here, right? You see the vector addition? The blue plus the red is the black. So in terms of an equation, that means that the projection of A, projection in the A direction of B, plus the orthogonal projection in the A direction of B, which is the orthogonal projection is not in the A direction, right? It's actually completely outside the A direction altogether, right? But this has to equal what? It's just B, right? This is what you want, and that means that we will define the orthogonal projection to A of B as simply equal to B minus, well, the projection into the A direction of B, right? Which, if you want a formula, well, it's obvious, right, from what's above, right? Now, the first thing to prove here, and we should take a second to prove it, which is that these are actually perpendicular for arbitrary vectors. Can we prove that? Now, I do all this stuff in Calc 3. If you take my Calc 3, you've seen this before. I mean, my notation's a little bit different there, but pretty much the same. So, like, we should see the projection in the A direction of B dot the orthogonal projection in the A direction of B. It should work out to 0, right? So how's that go? We have B dot A hat, right? A hat dotted with what? B minus B dot A hat, A hat. That's the projection dot the orthogonal projection. Now, properties of dot product give us that this is B dot A hat times A hat dot B minus, well, I'm going to factor out the dot product here, B dot A hat, pull that out, and then we've got, well, B, we got two of these B dot A hats, don't we? All right. And then we're left with A hat dot A hat. Do some color coding so you can follow me maybe. So let's say this one was that one, this one was this one, and tracking I had this dot that is that. What's A hat dot A hat? What is it? So you guys are not telling me. Right here, right? Try this out. What's a hat dot a hat? Yeah, we got a dot a divided by the length of a squared. But what was the length of a? Yeah, I mean, so that's a dot a over a dot a, and you're telling me it's 1, and that is correct. A hat dot a hat is 1. So then what do you got? Well, the dot product is commutative, right? So this is just 0. So that shows you that my picture is legit. It really is the case that this is a right angle. These are perpendicular vectors. So we can always decompose a given vector as a sum of a parallel component to another vector as well as a perpendicular component to that given vector. This is an old story. This goes back to like Euclid, right? With compass, straight edge constructions. You calculate the perpendicular bisector by taking compass and swiping stuff out. Like this is old. This is very old. But we have formulas, which is more new. Notice that this equation deserves a little bit more airtime. Let me just stop and say theorem A vector is equal to the length of A times A hat. Do you guys recognize the importance of this? What is this saying? It's saying any non-zero vector, right, can be written as a product of its magnitude and its unit vector, which you could also call its direction, right? Any vector can be written as a product of a magnitude and direction. This we should have heard somewhere before. Yes. Calc 3 or perhaps... Oh, Despicable Me. What's that? Sorry. I know what Despicable Me is. I admit it. I don't have if you ask me how many Despicable Me movies there have been, I can tell you a lot. I once paid for my children to see one of those movies, 3D. At the time, we were hosting a foreign student from Japan somehow, and I think it was over $100. Like, I remember that, and I don't feel like it was worth it. I mean, I don't know, but anyway, they're all fun. Don't get me wrong. Okay, so listen. So that's the concept, the basic concept of projection onto a single direction. Last time we were talking about projections not onto a single direction, but like onto, you know, more than that, right? So here's the next step in this story. And I haven't worked this out in a while, but I think it's worth returning to. This is 9.2.16. I'll write it out. If, let's say, I'm going to use vectors. If A and B and C are linearly independent vectors in Rn, then A prime, B prime, C prime is an orthogonal set of vectors in Rn if we define A prime equals to A, B prime equals to the orthogonal projection in the A prime direction of B, and C prime equals to the orthogonal projection in the A prime direction of the orthogonal projection in the B prime direction of C. So first of all, if you just have two vectors, do you see how the basic concept of projection already gives you a way of orthogonalizing? Did you guys, I guess I should probably start with that first before I get to this 3 thing. But it's too late. I've already written the 3 things, so my bad. But just think for a second with me. If I have two vectors A and B, right? And they're linearly independent, what would that mean? I'll put the comment up here. By the way, if we have A and B linearly independent, then A prime equals to A, B prime equals to the orthogonal projection in the A direction, A prime direction, B, gives A prime, B prime orthogonal, right? We just showed that right here. I guess we didn't exactly show that. I showed that, technically, I showed that the projection of A is perpendicular to the orthogonal projection, right? But notice that the projection and the vector are parallel. And if you have a third vector is perpendicular to a vector, then it's also perpendicular to any vector which is parallel to that vector. Let's see here, how can I say this? Well, anyway, let me not belabor that. So that's already a way we can construct an orthogonal set of vectors from a given pair of vectors. We can just take the vector and then find the orthogonal piece to it. There you go. That resulting set is orthogonal. Here's how to do for 3. Right? What's the formula here? This is what? B minus, how's it go? A prime dot B over A prime dot A prime, right? Times A prime. I mean, that's the formula for the projection I have over there, replacing A with A prime. If you remember back to last class, although I hate to say those words, that was the formula I wrote for the second step in the Gram-Schmidt algorithm. So the second step, the Gram-Schmidt algorithm is based on using orthogonal projections to projections. Like, that's the idea behind it. Check this out. So this one, we have, orth A prime. Now what's this? This is equal to B prime minus B prime dot C divided by B prime dot B prime, right? In the B prime direction. But how does that work? That's equal to the input vector, right? Minus what? Minus the projection. So that's I'll write it out here. Let me just write projection in the A prime direction of this vector here. So this gives me C prime is equal to B prime minus Oh. Oh no. You guys got to stop me. Is that right? Let's think. Think about this. The orthogonal projection in the B prime direction of C, right? We take C and we subtract the projection of C. So this should not be B prime. This should be C. Right? This right here is the projection of C in the B prime direction. That's what we're supposed to do. So that makes this B prime out here a C prime, okay? All right. And of course this is also C prime. All right. So putting it all together, we have C prime minus B prime dot C over B prime dot B prime, B prime, and then this projection piece, right? So minus, how's this go? We've got C prime minus B prime dot C divided by B prime dot B prime, that vector, dot A prime, watch this, all divided by A prime dot A prime, big old parentheses here, A prime. That's the projection in the A prime direction of that nasty vector there. And I lost a little something, didn't I? What did I lose? Look at the expression I've written. It doesn't even make sense, right? Can you guys see what's nonsensical about it? The first part. Can you be more specific? Well, I mean, this piece right here is just that again, and that I'm just copying up to here. So nothing happened there. But what about the projection piece, though? There's something wrong with the formula I wrote for this. Vector. Is this a vector? That's right, this is the ratio of two dot products. This is a number. What am I missing? I'm missing this B, and that was a B prime, so I'm missing a prime right here. So I owe you guys a B prime right there. That's important because what is B prime dot A prime? How did I get a C prime? That's not a C prime. Why is there priming the C's here? Doofus. Me, not you. That was not a C prime. We're defining C prime, idiot. Me, not you. So, good grief. This is why we cannot have. Oh, thank you. Oh. Thank you. So C dot A prime over A prime dot A prime. Is that what you're talking about? No? Oh. Well, you should have taken it. That was there for the taking. You could have claimed it. A prime dot B prime is what? By construction, these are orthogonal. The dot product of orthogonal vectors is, see this right here? 0. We just showed it over here. All right? Lo and behold, this right here is the formula for the orthogonal projection of the orthogonal projection. Now, you'll forgive me if I don't complete the proof. I guess the complete proof would actually be to show you explicitly. You guys will trust me. You can show that A prime dot B prime equals A prime dot C prime equals B prime dot C prime. These are all 0. All right. This set of vectors, so constructed, is necessarily perpendicular. And this is the Gram-Schmidt algorithm that I wrote in a different notation last class. All right. All right. So, the general theorem is if we're given S equal to V1 through Vk, a subset of Rn, linearly independent, then if we say, okay, so like V1 prime is V1, V2 prime is V2 minus V1 dot, let's say V1 prime dot V2 over V1 prime dot V1 prime, V1 prime, etc., until we get to like the jth one, Vj prime is equal to Vj minus the sum I equals 1 to j minus 1 of Vi prime dot Vj divided by Vi prime dot Vi prime, right? Then S prime, which is V1 prime, V2 prime, dot 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 Vk prime, is orthogonal. This is the Gram-Schmidt algorithm, and it just comes from like repeated orthogonalization, basically, of your vectors. And then, of course, we could define S prime prime, V1 prime hat, V2 prime hat, dot 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 Vk prime hat is orthonormal. In other words, Vi prime hat dot with Vj prime hat is Kronecker delta Ij. It's horrible notation, isn't it? I've been using like V1 prime prime and V2 prime prime last class for the normalized versions. So the larger point of all this is simply this. Theorem, given W is equal to the span of beta, where beta is equal to, say, let's use W1 through Wk, is linearly independent. This makes W what we call a subspace. A subspace is a subset of our, for us a subspace is a subset of Rn that's closed under vector addition and scalar multiplication. It's like a line or a plane or a volume or whatever else through the origin. It's essentially a copy of k-dimensional space embedded in Rn. So we in this context, we say the dimension of W is k, all right? So what I've just showed you guys is that then there exists, let's say, gamma V1 through Vk such that Vi dot Vj is equal to Kronecker delta Ij. So this is an orthonormal basis. For W. So okay, like I haven't, what's the proof of that? Not that this is a proofs class, but like you can appreciate the proof with me. It's not hard to understand. Here's the proof, guys. Given beta, run the Graham-Schmidt algorithm to obtain gamma. That's the proof. You take the linearly independent set, you run the Graham-Schmidt algorithm, voila. You've got a linearly independent you've got an orthonormal set. Why do we care? Well, orthonormal sets are very nice, of course. Right? In fact, there's a larger theorem. In fact, we can obtain basis, let's say beta, I'll call it beta prime since I've already used beta. What do I got? I got beta, I got gamma. You know what we haven't used yet? Upsilon. So there exists a basis upsilon for Rn such that upsilon, all right, is equal to the gamma I talked about above, unioned with, let's say, Vk plus 1 all the way out to Vn, orthonormal. In other words, I can actually keep adding vectors to the set I have for the basis of W, and I can get a basis for all of Rn, such that they're all pairwise perpendicular in length 1. And it's with respect to that basis that I built the projection formulas last time. Like the formula, the projection into the W subspace of X is like the sum I equals 1 to K of X dot Vi, and the orthogonal projection to W of X is the rest of it. The sum I equals to K plus 1 to N of X dot Vi. So these are the projection and the orthogonal projection. That gives me the shadow of the vector X into the subspace W, and also the piece which is perpendicular to that space. All right. And I tried to show you how those formulas worked last time, and I'll probably post the videos, but I may need to post I'd like to actually give you a decent example of this in action for a non-trivial example. I'm not going to try to do it today because I'll just mess it up right now. So let me not do that. But all we're doing there is extending this idea to like a higher dimensional subspace. Now, all right. So I mean, I personally think studying geometry in higher dimensional context like we're doing is interesting in its own right, but there is a application of what we're doing that's actually very interesting and important to applications. And so I'm going to shift gears here and go to that. Now I think in order to explain what I want to explain next, which is called least squares regression, I need to remind you something we proved last class, right? Last class we explained about the perp to a subspace, remember? we talked about the orthogonal complement to the subspace last time, and we proved a little theorem there. I'll remind you. So last time we introduced for S, well, let's just say for W perp was equal to x in Rn such that x dot W, little w, is equal to 0 for all W in W. And there's a theorem that says that, well, let me just say, by the way, if W is the span of beta, then and beta, let's say, is V1 through Vk again, then beta perp is, what beta perp means what it means, right? Which is x in Rn such that x dot Vi equals to 0 for I equals to 1 through k. All right, well, the theorem simply says that that's also W perp. So you can calculate the perp, the orthogonal complement to a subspace, either by simply maintaining perpendicularity to the basis, or you maintain perpendicularity to all possible vectors. Either way, you get the same orthogonal complement. This is the orthogonal complement to W. All right. So last time we saw if S is equal to, like S1, S2, say k things, right? Then the orthogonal complement to S was what? It was the null space of what? Then I think you're on the right track there. It was the null space of the matrix formed by S, right? Transposed. So this matrix of S was, just the S vectors glued together to make a matrix, right? This is an n by k matrix, right? S transpose is literally a k by n matrix. And the null space of that, as we proved last time, is in fact the perp to S. Let me just capture this theorem. Let me just restate this theorem using a matrix A, okay? So like, if I just translate the same result, we have this, that the null, let's see here, how can I say this? The null space of A transpose is the perp of the, is equal to the column space of A, the perp of that. So I'm just putting basically, I'm just putting this equal to A. Okay, admittedly, I am also using the theorem up above because, like, the column space of A was what? It's the span of the columns, right? For instance. But anyway, the null space of the transpose of A is the perp to the column space. And if you just make a substitution into this, you can also see that the null space of A itself is actually the row space of A perp of that. Ooh, I'm sorry. I shouldn't. We don't do row vectors in here. Let me not do that. That's an artifact from an earlier time. Let me not write that down. I don't think we even need it. So we'll stick with this. All right. By the way, I do have some examples of Gram-Schmidt I'll show you. I want to use the projector for them because it's just a bunch of tedious arithmetic, and if I try to do it on the board, we know what's going to happen. So, yeah, I'll have to make another video, exactly. All right, so let me try to make us a picture of the, let me set the stage here. The problem of least squares data fitting is that you have too much data for your model, basically. Your model maybe has, 3 parameters or something, but you've got, I don't know, 300 pieces of data, whatever. And the likelihood that you got 300 data points and there's an exact fit to your model, which goes through all 300 data points, is like very, very small. Let's think smaller. You've got a model which is linear, like in the 2-dimensional sense. So it's of the form y equals mx plus b, right? You got 3 data points. Do 3 points lie on a line? I mean, maybe. Probably not, though. So then you're left with this question of, okay, well, if we can't solve the equations directly, then what do we do? Right? What do we do when we can't actually solve a system of equations that's linear directly? Like, what do we do? What's the next best thing? Well, the next best thing is to approximate the solution. So let me try to draw you guys a picture of this idea. And I do actually have examples with models and data and stuff, which I'll project here at the end of class, but we need to set up the problem here. So here's the basic problem is this. We're trying to solve ax equals to b, where we're going to be pessimistic and say b is not an element of the column space of A. All right. What does that mean? What is AX? AX is a linear combination of the columns of A, right? So if it's not possible to build B as a linear combination of the columns of A, that means that B is not in the column space of A. Here's a picture. So this here is, column space of A. And here's B. So there's 2 pieces, right? We can talk about, I should have used different colors. So we've got the piece which is perpendicular to the column space, right? And we've got the piece which is in the column space. So this would be what? The projection into the column space of A of B. And the other piece is, of course, the orthogonal projection into the column space of A of B. So this point right here, that's a point which we can solve for. Like, in other words, if I look at the equation, let's say A times U is equal to the projection into the column space of A of B, this right here is consistent. Why? Well, the projection into the column space of A is by construction in the column space of A, right? Like, this is an element of the column space of A. How do I know that? Well, you know, if the column space of A is, you know, the span of W1 through WK, then what is the projection of B into the column space of A? Well, we just talked about it a second ago. It's literally the sum I equals 1 to K of B dot W sub I times W sub I. We're taking all of the vector projections of B and adding them together to get the shadow of the vector B into the column space. Now, I need to assume something, right? Don't make the mistake I made last class and not use an orthonormal basis. We need that W1 through WK to be orthonormal for this formula to make sense, all right? But it should be clear, though, that that is an element of the column space of A, right? Can you guys see that? I mean, this is an element of the column space of A. And if you go back to the earlier part of the course, we proved, actually, that you can solve a system if it's in the column space of the coefficient matrix, right? So I can't solve the given problem, but I can solve a corresponding problem. So what does that mean then?
That won't give you X.
It won't give me X, but it'll give me the next best thing. Let's see why that is.
Oh wait, because if you add U plus the 4.
Yeah, let me try to make that precise. Give me a second here. So here's a proposition 9.5.1 from page 232. And it says this, that AU equal to the projection onto the column space of A of B minimizes the norm, the length of AX minus B squared. And here's the calculation. If we look at the distance between AX and B for any X, then we can rewrite that as the length of AX minus the projection onto the column space of A of B plus, I lost my place, rats. Oh, minus the orthogonal, duh. So I'm breaking B into its, just like here, all right? Like B has two pieces, right? It's got the piece which is like this, yeah? And then the other piece, like in my picture, and the other piece is like this, yeah? All right, so here's the deal. This right here, this is in the column space of A. This right here is in the column space of A perp. In other words, these vectors are perpendicular. I think I proved earlier in the semester that if we have two perpendicular vectors and we add them together, the length of their square, the squared length is the sum of the squared lengths, right? This is the Pythagorean theorem. So like this is equal to this is the Pythagorean theorem. If we have two perpendicular vectors, the length of their sum squared is equal to the sum of their squared lengths. So as we think about the norm of ax minus b squared, right? We're stuck with this. We can't do anything about that. But we can make this as small as possible by making this 0, right? When is this 0? It's when x is equal to like the u over there, right? When we have au is equal to, if I put x equal to u in the sense over there, that makes this 0, which makes the error, this is the error, right? Error in x. So if I put setting x equals to u, where, you know, au equals to the projection onto the column space of A, of B, minimizes error.
So you're saying there's no way to actually get x, but you can get...
That's, oh, yeah, I mean, it's an impossibility. This is an inconsistent system. Inconsistent means no solutions. Yeah, there's no such x. But this is x equal to u is the best approximation to ax equals to b in the sense that the distance from ax to b is as small as is possible.
How does that help?
It gives you the best approximation to the system. So if you can't fit a line through 300 data points, you find the best fit line. This is the mathematics of that, yeah.
Should you use limit notation?
Limit notation? Well, maybe, but no. No limits. No limits in here.
Isn't that basically what you're saying, though? It's like the closer you get to...
Speaking of no limits, I'm thinking of adding a arm wrestling component to my math battle in Calculus 3. What do you think? I'm going to have to break the class up. They're all doing the same. They're all going together on the same team. I need to break them up because in order to have an arm wrestling competition, you have to have different teams, obviously. And to even it out, girls get to use both arms. Seem fair? Seems all right, right? Yeah? 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 Some resistance. Oh, that's, you are a connoisseur of the arm wrestling. Very good. So, now, listen, this doesn't seem particularly helpful in terms of a calculational method at the moment, because if you look at what I've done, I've said, oh, so how do we find the projection onto the subspace? What do we do? What's the cost? The cost is you have to find an orthonormal basis for your subspace to build the projection formula, right? Is it easy to find an orthonormal basis for a subspace? Yes and no. I mean, it's a pain. Gram-Schmidt algorithm is tedious. So at first glance, this wouldn't seem to be terribly helpful because it looks like we'd have to orthonormalize a basis in order to put this into action. So what's about to happen is simply amazing. Like the next thing I'm going to show you is really, really cool. These are the so-called normal equations. It's really too good to be true. Because the normal equations say the following. They say that we can trade theorem AU equal to projection onto the column space of A of B is the same as A transpose AU equals to A transpose B. So instead of actually having to calculate the projection, as much as I love to do that, we don't have to once we prove this theorem, because we can solve the normal equations. Normal equations are easy to come up with. Let me show you why this is true. It doesn't take long, if I can find my proof. I did put a sticky on there. Where'd it go to? Come on. Sticky notes, don't let me down now. You got to know your weaknesses. And I know that if I'm not careful, I can make this proof last a long time. But there's no need because it's actually very simple. If you can find the proof in your notes. Come on. Look at that stupid thing. Oh man. Am I going to have to think? It's starting to look like I'm going to have to think, guys. You know, that's dangerous for me. Well, it's probably the one I'm holding in my hands. Nope. Wait, what? Ah, finally. I didn't put a sticky note on this page. I'm an idiot. All right, anyway. Okay, so here we go. Proof. So AU equal to the projection onto the column space of A of B. All right? If and only if B minus AU is equal to B minus the projection on the column space of A of B, right? So I subtracted AU from the left-hand side, and I subtracted the projection from the right-hand side. You guys see that? But what is the right-hand side now? Can you recognize? What is that? What's that? Very good. That is orth of the column space of A of B. I regret not calling the column space of A W like 10 minutes ago, because I've written column space of A like no less than 20 times. But anyway, there it is. That's orth. All right, great. But this is going to be true if and only if B minus AU is an element of the column space of A perp. Right? That's what the orth does, is it puts you in the perp to the column space. But we have a characterization of that in terms of the null space of A transpose. So that means B minus AU is an element of the null space of A transpose. But what does it mean to be in the null space of A transpose? It means that when you multiply that vector times A transpose, you get a big fat 0. Which of course is the same as A transpose B is equal to A transpose A U. And these are the normal equations. Notice that the normal equations don't require us to actually get into the details of the projection. We don't have to Gram-Schmidt. All we have to do is take the inconsistent system and simply multiply by the transpose. Multiply by the transpose of the coefficient matrix, and through some, act of God's providence, we're left with a system that we can solve and find the best approximation to the unsolvable original system. All right? Let me work out one of these examples by hand. And then I'll show you some ones with the projector, but we should do one by hand at least before I project. So let's think about the problem I was talking about. You've got a line. You want to find y equals mx plus b closest to the data points, let us say 1, 2, 2, 3, -1, 7, and I don't know,